So now we've made inference by either just estimating the population value, in the case of the mean or the standard deviation, and with confidence intervals. Now we're going to look at another popular method of making inference. It's called hypothesis testing. What we have is what we call the hypothetico-deductive method that we've been using for almost 200 years now to increase our knowledge in science. So Karl Popper called it the essence of the scientific method, which is, number one, set up a falsifiable hypothesis. That's the difference between science and other forms of knowledge. The hypothesis you set up must be falsifiable. Doesn't mean you're going to falsify it, but it must be falsifiable. And then step two, design your experiment, get your data, etc., to test your hypothesis. This, of course, because we're going to use inference, there's going to be uncertainty. There's always uncertainty in our inference. Let's take a look at an example of what we're talking about. So, for example, we know that the total cholesterol levels in our population are distributed with mean mu of 237 and standard deviation of 44.7. We know that. Set that aside for a minute. Now, suppose somebody approaches us and says, okay, I've got a sample of 49 cholesterol levels, and the sample mean is 230 milligrams per 100 milliliters. Is it possible that these 49 actually came from your Framingham population, or came from a population with the same characteristics as your Framingham population? Is it possible that we could take a sample of 49 from your population and come up with a sample mean of 230? Maybe what you would do is say, okay, standard deviation 44.7, you're taking 49, the square root of that is 7, 7 into 44.7 is about 6 and a half, so 230 is one standard deviation away from 237, and so the central limit theorem tells us that what we're talking about is quite possible. It's a likely event that will be within plus or minus one standard deviation of the population mean. So it would be reasonable in this case to assume that this is a sample from our population. What if instead of 230 we'd said 223? So somebody comes to you and says, here we go, 49, and their mean is 223. Is this possible? Well, you did the calculations, was about, what did we say, about 6.5. So now we're 2 standard deviations away from the sample mean. 2 standard errors, sorry, away from the sample mean. So maybe you're trying to start thinking, well, what if they come with 215? Now you say, oh, wait a minute, this is much too far away. I expected things around 237, and now you're giving me 215. Now you might wonder, is there another possible explanation? For example, was this group that you're measuring on some cholesterol lowering regimen? Maybe exercise, maybe diet, maybe popping a pill of some sort. Is there some possible other explanation? In summary, we could possibly use the 95% confidence interval to infer values of mu. So if we did our calculations, we see that standard deviation of 47.7, sample size of 49, so x bar plus or minus 13.4 gives us our confidence interval for the population mean mu. So this has a 95% chance of including mu. So that when the person came to us with a sample mean of 230, that gave us a confidence interval of 216.6 to 243.4, which certainly includes the 237 in there. So the answer would be, yeah, it's possible. It's quite possible. that when we take a sample of size 49 from this population, we would get a sample mean of 230. The second sample was at 223. Now, look at our confidence interval. Now, this bangs on that, and in fact, the 237 is not in there. So we're starting to worry about it. And in fact, when we got the sample mean of 215, we see that the confidence interval does not include 237, so we're much less likely to believe that this indeed was a sample from such a population. So we could use confidence intervals to answer the question we were faced with. Namely, is this sample, whichever one of these three we choose, possible to be from this population? By possible, I mean level of uncertainty, or level of certainty of 95%, as incorporated in our confidence interval arguments. So in summary then, we can ask the alternative question, which is, if we have a population with a mean of 237 and a standard deviation of 47.7, and we take a sample of size 49 from that population, then the central limit theorem tells us that the sample mean is approximately normally distributed. The sampling distribution of the sample mean is approximately normally distributed with mean 237, the same as the population mean, and standard deviation or standard error of 47.7 divided by square root of 49, which is 7. What that means is that when we subtract the 237, divide by 47.7, we get a standard variate, Z, that's going to be between minus 1.96 and 1.96, 95% of the time. And then when we do some arithmetic, that means that the predictive interval for our sample mean is 223.6 to 250.4, 95% of the time. So look at the sample mean offered. If it lies between 223.6 and 250.4, then you can say, oh, an event that I predicted would happen 95% of the time has happened. Alternatively, if we get a sample mean that is not within these bounds, is less than 223.6 or greater than 250.4, then we say, wait a minute, something unusual has happened. Namely, I could be in that 5% domain where something unusual has happened, or my if is not correct. The premise that I've set up here is not correct. So one of those two situations has occurred. If we get a sample mean that's outside these limits. These two approaches, namely, look at the confidence interval and see if that covers the hypothesized mean, in this case 237, or look at the predictive interval and see if what you've observed falls within the predictive interval or not. The conclusions you come to in those two situations, these two approaches, are completely consistent. They're consistent with each other. I know that there's some people who would tell you otherwise, but it's not true. Those two approaches are completely consistent.